This meeting is being recorded.
All right, it's all yours. Take it away, Larry.
All right, I got it. It said I'm recording. I really had a lot of fun preparing this today because it's been a major part of my life, and I really look forward to sharing it with you. And if you mute all your microphones, and I will go through a slide presentation with, I go through pretty rapidly with a few small stories. And one of the stories is right here behind me. You see the picture of Alan Bean and one Snap 27 generator. So with that, let's get started and look forward to sharing this with you. And personally, I graduated way back when in '64 in mechanical engineering design with a minor in marketing, and I'm so glad I had that. It became a major part of my life, and joined Solar immediately, which greatly influenced my total career. I spent the first year learning about brazing, and the second year was promoted to research engineer and supervisor of Beryllium Fab Lab, and later on manager. But I'm going to take you through that first year is where I learned about brazing, and I worked with a great guy, Jim Woodward, who was one of my mentors at Solar. And here we were designing and building space mirrors out of Invar material on a classified program at that time. And these were massive.
Recording in progress.
Don't know where the feedback is coming from. Okay, and beryllium that we're going to be talking about today is number 4 on the periodic table. There's 2 gases, hydrogen and helium, before it. So it's a very unique material. And the way I heard about beryllium was on a Sunday morning, about 4:30 a.m. in the morning, I get a wake-up call from George Kramer, who was the director of the manufacturing technology group within the Solar Research Department. Larry, got great news for you. We just won the nuclear powered generator, the Snap 27, that's going to go to the moon from General Electric, and I'm calling you from Valley Forge, Pennsylvania to share that news with you. And I said, George, that's great news. He says, Larry, that's not great. What's great is it's going to be made of beryllium. And I said, beryllium what? And he said, I'll explain it all to you Monday morning. And Monday morning, we went into a classified room, no windows, shut the doors, locked the doors. He says, Larry, we're going to buy precision component A from company A and precision component B from company B, put them both together and braze it. And I said, well, that's great, George. I knew what the word braze meant. I said, George, how do you braze beryllium? And he said, Larry, we don't know, but that's going to be your job. I said, really? He said, yep. He says, and you are going to be supervisor of a brand new laboratory, and it's going to be called the Beryllium Fab Lab. I said, well, George, I said, all the building is full of the research department. Where's this going to be? He took me down the main street to the main lobby entrance. And he said, Larry, look at this. History was made in this building. There's a plaque up there. The Spirit of St. Louis was built in this very building, and you're going to make history here too. We went inside through the machine shops, up the stairs, into an attic, into a room in the attic that measured about 10 by 20 feet. He said, Larry, this is your new laboratory. And I look around, there's no electricity, there's no gas, there's no equipment. I said, George, there's nothing here. He said, Larry, I told you you're going to be supervisor. And so the first guy that is going to be working with you is Lowell Kemper, and he is the best acquisitioner that anybody in this company who will have it outfitted in a week. And sure enough, we did. And from that, we started our work on beryllium. And to give you an idea of what beryllium kind of behaves like, in this little presentation, this is magnesium here. This is aluminum, magnesium, and a beryllium, and weights are on the end, and they're a cantilever beam. And here's what happens when you pull out the structure from underneath it. You can see the other metals just vibrate and dip down, whereas beryllium is stiff and straight out and solid. And keep in mind that this particular slide is showing that the beryllium is really not pure beryllium. It's only 60% beryllium. It's an alloy that we developed for later on the beryllium industry and the disk drive industry, but it wasn't available at the time. And this gives you another idea of its weight characteristics. That block of beryllium that you see there measures about 4 inches by 5 inches by 20 inches and weighs over 30 pounds. If that was steel, that block would be 150 pounds. And yet that little diameter thing at the bottom, about a 1/2 inch diameter, is made from beryllium, and it weighs only 0.4 grams in supporting that entire structure. And 53 years ago, when we landed on the moon, it carried Solar's hardware and that we helped design and build, and it was really remarkable. I'm going to start at the moon landing and then work backwards how we got there. You know, every time I see this, July 20th, 1969, it's just an amazing feat. Like you said, hey, these guys were pretty damn brave to get on the lowest bid satellite and structure and fly out there and make it happen. And here you see a photograph of Alan Bean on the moon. And this is where the plutonium 238 is. It's red hot. He reaches in with a handle, takes it out, and puts it down into the center of the Solar Snap 27 generator. It's called nuclear powered because the plutonium 238 is the driving factor for it. But at that time, Dave and his sister Susie were pretty young kids, and we watched this on TV, and I tell you, it was really, really exciting. Now, how did this all start? The first task we had to do is learn how to braze beryllium, and it started with this little tube furnace. It's a clamshell furnace, and this is Pyrex, and a tube to put inert gas in, and an optical pyrometer to measure temperatures. And we would watch as alloys would start to melt, and we had perhaps 200, 300, 400 experiments. We would be running experiment after experiment and looking at the results and then changing things. It started with just 2 of us in this little 200 square foot laboratory. And from there, it went to 30 of us in 3,500 square feet. From there, we scaled up to something larger, using a retort to protect the inert gas and making larger samples. The laboratory had expanded by that time. We bought in some bigger equipment and running some larger tests. One of the tests we had to do was develop the joint for joining the beryllium to stainless steel, because the entire cylinder had to be under pressure, 25 psi of argon, in order for it to work. If the argon leaked out, the generator would stop producing because there's a vacuum and it's not conducting the thermal energy from the inside. So we developed this joint and we tested it by welding a 1/4 inch thick plate onto the little thin transition ring and exploded it in a test chamber. And we went up to 525 psi with a great margin of safety. And one of you had mentioned about beryllium, a potential health hazard. And at that time, we had to put a warning label on everything that went outside of our laboratory, so nobody in the Solar shops would start machining on it, because the potential health hazard is the fine airborne particles and breathing it that goes into your lungs. And Solar had very strict health and safety regulations with good ventilation and equipment. We had our own met lab upstairs to do the metallurgy. We would prepare this sample and then take it downstairs to the Solar Research met lab to take the photomicrographs. This is a test of one of the Solar fins. Bill Shoemaker here is running the test, measuring the temperatures, where we would put a heater and heat this up to 525 degrees F, and then measuring how the heat radiated out from the fins. This is a slide that kind of shows you the progression of what Solar started with. We purchased beryllium raw material from Brush Wellman and Kawicki Beryllium, This cylinder, if you took this diameter and this length, represented about 60 pounds of beryllium. That's a big chunk of metal. In today's market, that would be $60,000 for this piece of raw material that then got machined down to this shape, and we would sell the center back. That's worth about $8,000 just to sell the core back to the raw material supplier. This was machined in Sarasota, Florida, as a subcontractor for us, is the central cylinder. And the fins were produced from taking a block of beryllium and then rolling it into crossroad sheet, and then the fins would get brazed onto the cylinder. Solar also produced the stainless steel hot frame that the plutonium slid into, and the stainless steel caps, the transition ring, and the joint. And give you an idea, the cross-section of the generator is the fins, the cylinder, and the guts of it is here. I'll show you in the next slide how that came together. This was capable of producing 60 to 70 watts electrical power, and how it did it is by putting in plutonium in the center, which is red hot. And so this cylinder surface right here on the inside was 1650 degrees Fahrenheit. And the outside cylinder of beryllium was 525 degrees Fahrenheit. By using lead telluride, positive and negative thermocouple leads, and connecting them all in series and parallel, they get the electrical power that they needed. Here's a picture of us doing a preliminary assembly. One of my technicians, Clyde Shear, and this is John Long, the director of research. And an interesting story about John. John was a naval guy, naval officer, and every Friday afternoon he would walk through every laboratory in solar research and give it an inspection. And boy, you better have your decks cleared and things shiny and cleaned up every Friday afternoon. And one hot summer day, he came into the Beryllium Fab Lab and he took off his jacket and he looked around for some place to hang it up. And there was no coat hanger. And he said, "What's the matter with you guys? You don't even have a coat hanger for a guest?" And that was Friday afternoon. Monday morning, I came into the lab and lo and behold, there's this beautiful coat rack. And I said, "Lowell, where did this coat rack come from?" He said, "I don't know, Larry, it just showed up." And remember, Lowell was the best acquisitioner that we have in solar. And then I started hearing rumors that John was really pissed. His coat rack was gone from his office. And he was furious, but it wasn't until Friday afternoon that he came up to inspect our lab. "My goodness, you guys got a coat rack. It looks just like the coat rack I used to have. Well, I'm glad you got a coat rack, and I still have that coat rack today." And this is the assembly of the outer assembly, the fins, and here we're putting in titanium as a getter to absorb the oxygen. And this is a graphite cylinder that kept everything lined up during the precision brazing operation. And this young man, Terry Greenlee, was a young student that came to work at Solar for one summer. And he was so grateful for that experience. He contacted me about 2 years ago after losing contact for many, many decades, and just to call and say thank you for that experience. He went on to get his PhD and is retired now, but he still remembers his days at Solar. During the big brazing operations, some of you know about the V2 furnace, V1, V2 furnace, these giant furnaces that are up in the sky. And this is the retort that the Snap 27 generator was in. And we had all these lines coming down to this control panel that we could monitor the temperatures, the pressures, bring in and out the gases and keep it under positive pressure. And we designed all of this in the Beryllium Fab Lab and built it. And this whole process of going through this cycle was approximately a 2-day process. From the time we loaded it in, got it there, got the temperatures, rammed it up, heated it up, and then the cool down cycle. Jim Woodward and I, this is an assembly before it was black ceramic coated, and it was black ceramic coated for high heat emissivity. And that was also done in the ceramics lab at Solar Research. And this photograph is obviously my favorite. And there's 5 of these nuclear power generators on the moon right now. And if you think about the half-life of the plutonium-238, it's like 88 years. So right now, those generators are still producing on the moon today like 13 watts of power. If you've ever been to the Smithsonian or you're planning to go, there's 2 solar-produced SNAP 27 generators on display at the Smithsonian. And of course, there's one right here behind me, which was part of my purchase when I purchased the Beryllium Fab Lab from Solar. And right after we finished doing the SNAP 27 production, other people started learning we knew how to braze beryllium. And so we got this program from iTech to build a camera housing for the Viking lander going to the Mars. And this is the first photograph taken out of the Solar produced camera housings for Mars. And then the visible infrared spin scan satellite for Santa Barbara Research came to us, and we designed and built the main support ring for that satellite. And this is a very interesting story from Hughes Aircraft. Hughes was in the process of designing a communication satellite, a very large communication satellite. This is like 9 feet in diameter across here. And the primary structure of the spin scan satellite was this I-beam structure that was built from 4 J channels like Bill Shoemaker is holding here. And I was fortunate enough to be invited to be part of the team that went up to Hughes Aircraft to make our pitch on doing this in beryllium. And after we made our pitch, the engineers at Hughes said, that's impossible. You guys can't do that. You cannot achieve the flatness and the straightness that we need for this structure. That beam has to be flat within 10 thousandths of an inch per foot and straight within 10 thousandths of an inch per foot. And we said we could do it. They didn't believe us, and we got on a plane and we headed home. And when I got home, I said, gosh, how are we going to prove to Hughes Aircraft we can do that? I said, the only way we could prove it is to build a physical, actual beryllium U-channel. And I was home that night. David and Susie, they had lots of toys around. They had some blocks, I had some balloons, I had some paper. And I took a block and I took a piece of paper over it, and I took one of the kids' balloons and I pressed on it and the folded over, and I said, wow, that might just work. And the next morning, I took my kid's block and my kid's balloon, and I went to Solar, and I went to George and Jim, and I said, guys, we can do this, and we can do it in 2 days. We can build a precision beryllium U-channel in 2 days, and here's how we do it. Now, I've never shared this slide with anybody. In fact, Dave was even amazed when he saw this. He said, I've never seen that. I said, well, it's okay to share this technology today. And here's what we did. We took a piece of tool steel and we took it to the machine shop and had a machine some radiuses on it. In parallel to that, we took some 3 thousandths of an inch thick stainless steel and welded it up into a flat inflatable balloon. And because we didn't have at that time a tool, an upper mandrel, lower mandrel, we drilled some holes, tapped them into the steel. We took another piece of steel up here, drilled some holes, drilled a hole in the steel, in the beryllium. We bolted it all together, shoved the thing into a furnace, heated it up to 1350 degrees Fahrenheit, turned on the gas, inflated the balloon, and lo and behold, out came this very channel that you're looking at right here. And those are the holes that held the whole thing together. And we flew up to Hughes on the 3rd day, put that beam on their desk, and they said, you got the contract. And Solar got the contract to build this. And they said, since you're so damn good, we're going to give you the contract to build this too. It was incredible. They begged us to go in and see how we were doing it. We wouldn't let them in. It was a secret room. That's a 9-foot diameter beryllium cone built by Solar for Hughes' first communication satellite. Then we started working with NASA on developing beryllium honeycomb panels for the space shuttle. And this is part of the team. And this is the beryllium panel with beryllium core made out of very, very thin beryllium foil, beryllium sheets, all brazed together. This is a NASA rep looking at, we built this in the Beryllium Fab Lab. And there's more I'm going to share about this beryllium for the space shuttle in a slide or two later. This is the building that Solar, where the Spirit of St. Louis was built. And this is where George Kramer stood with me and told me history is going to be made, and went right through those doors. We developed some classified programs building precision beryllium frustrums. And during this time, I asked John Long if I could work on my master's thesis. I was going to be in engineering, and I wanted to do a master's thesis on brazing of beryllium. And he gave me permission so long as I did it after hours and I didn't interfere with the work. And I was working long hours for Solar. But I found time to run my experiments. And this particular furnace was 440 volts, but it had an open elements. And as I was putting my can in with the inert gas, and I was reaching up to the top handle and holding the metal in the bottom one and closing the lid, and a micro switch over here turns the power on, and wham, I got 440 volts from left arm down through the body to the right arm. And fortunately, it threw me back and it opened the circuit, and I'm laying on the ground about 20 feet behind me. And of course, this is at night, nobody's around. I said, man, that was close. That was stupid. And I get up and I just kind of get myself together, and security walks through the door. Grant, what the hell are you doing in here working alone? You know that's against regulations. I said, oh, I'm not working, just picking up a few papers. I'm out of here. That was the end of that one. After I left Solar, I joined Lockheed Missiles and Space in 1972 because they were designing the space shuttle in beryllium. Perfect for me. My master's thesis was in beryllium. I'd graduated with my graduate degree. I'm their man. And 2 months after I quit and joined Lockheed, NASA said, there shall not be any advanced material in the space shuttle like beryllium. And I said, well, there goes that career. That was sure a great one. About 3 weeks later, I get a call from a very dear friend, Mr. Ken Olson, that I didn't know at the time, but he became a very dear friend. He said, are you Larry Grant, formerly of Solar and the Beryllium Fab Lab? I said, yes, sir, I am. He says, we need to talk. And lo and behold, Solar announced they were going to sell the Beryllium Fab Lab. And Ken Olson and some financial people put together a proposal where we were going to buy it. And I walked back into Solar 1 year to the date that I left Solar as a corporate officer of a new corporation to set up and use that technology. We hired many of the people from Solar, all the equipment, all the technology, all the work in process we took over. And here's where Solar's technology continued on from that point on. We built the hardware for the Voyager mission going to Jupiter. And here is some of the beryllium components that we designed and built and delivered. This unit was a radiator that was 67 detailed parts brazed in one furnace brazing operation. And the Voyager 1, Voyager 2 are still out there in deep space. Beautiful photographs. Every time I read these scientific reports of the photographs that come back from these space programs is amazing. And the new Mirrors shuttle satellite that they just launched has beryllium mirrors in it. I didn't have anything to do with that one, but it still makes my heart beat. Galileo spacecraft, we designed and built beryllium tubes. We developed technology to braze titanium to the beryllium. But what an exciting career when you see satellites being launched and going up and producing beautiful photographs. This unit for the High Energy Astronomical Observatory was 432 parts brazed in one furnace brazing operation and only 2 kilograms total weight. And the star tracker below it, beryllium. And to give you a relative idea of the size of this, that piece that that man was holding is right there. And this is the size of the entire satellite. Some of the first photographs taken from the High Energy Astronomical Observatory. Beryllium tubes, beam pipes for accelerator laboratories all over the world. And space satellite structures, this was for India, weighed 37 pounds, and it's a primary structure for loading satellite structures. It was launched by a space shuttle. This was for Japan. The bottom ring that you see here was flat within a thousandth of an inch. The upper ring was round and concentric to the bottom ring within 10 thousandths of an inch. And the purpose of that is to take the entire launch load of the satellite where the rocket is connected right here, and that yellow, or this beryllium cylinder in yellow highlighted, takes the entire launch load and everything is attached to it. This is a beryllium optic structure, flat within a quarter of a wavelength of light, and only weighs 2 kilograms, and it oscillates like this for your weather satellites. Optical support structures, gimbals, rings. I use this slide to show how young we hire technicians, but really it's to show how light it is. Solar array support beams. Here's where those beams were used in satellite structures for communication satellites. Tubular structures. This was for a program of space. And imagine she's holding that with just one hand, and that's the equivalent of a sheet of plywood in terms of size, 4 by 8 feet. So beryllium has played a very, very big role in space, and solar technology kind of led the way. Today, beryllium is being replaced with carbon fiber, graphite epoxy things for these kind of structural applications, but it's still extremely important for nuclear applications, for X-ray windows. Every X-ray machine in the world has got a beryllium X-ray window. And just postscript, in 1990, Electrofusion Corporation was sold to Brush Wellman, and they were our raw material suppliers. And my wife Scarlett and I founded a new company, US Grant Technology Inc., and it's still flourishing today in USA and China. And FYI, Larry and Jim, we spent over 5 decades until his death in 2018 sharing good times together, even though we had both left Solar. We maintained that friendship. This is Jim at his retirement home, where Jim and I gave a technical talk to about 80 retirees, and they were just fascinated by this technology. And we kept contact in other places. Here's George Kramer and Jim Woodward, myself, where we all went flying in a Ford tri-motor. You know, we kept this friendship going for years, and it was an incredible adventure. I've included in the presentation lots of references. Many were published while I was at Solar and some after. Some of the missions that we went on. And I just want to say thank you. It was a lot of fun being part of space programs, and a lot of fun being part of the Solar family. So with that, we can open it up for some questions.